A cyclic redundancy check is an error-detecting code commonly used in digital networks and storage devices to detect accidental changes to raw data. Blocks of data entering these systems get a short check value attached, based on the remainder of a polynomial division of their contents. On retrieval, the calculation is repeated, and corrective action can be taken against presumed data corruption if the check values do not match. CRCs are so called because the check value is a redundancy and the algorithm is based on cyclic codes. CRCs are popular because they are simple to implement in binary hardware, easy to analyze mathematically, and particularly good at detecting common errors caused by noise in transmission channels. Because the check value has a fixed length, the function that generates it is occasionally used as a hash function. The CRC was invented by W. Wesley Peterson in 1961. The 32-bit CRC function of Ethernet and many other standards is the work of several researchers and was published during 1975. Introduction: CRCs are based on the theory of cyclic error-correcting codes. The use of systematic cyclic codes, which encode messages by adding a fixed-length check value, for the purpose of error detection in communication networks, was first proposed by W. Wesley Peterson in 1961. Cyclic codes are not only simple to implement but have the benefit of being particularly well suited for the detection of burst errors, contiguous sequences of erroneous data symbols and messages. This is important because burst errors are common transmission errors in many communication channels, including magnetic and optical storage devices. Typically an n-bit CRC applied to a data block of arbitrary length will detect any single error burst not longer than n bits and will detect a fraction 1AAA2AN of all longer error bursts. Specification of a CRC code requires definition of a so-called generator polynomial. This polynomial becomes the divisor in a polynomial long division, which takes the message as the dividend and in which the quotient is discarded and the remainder becomes the result. The important caveat that the polynomial coefficients are calculated according to the arithmetic of a finite field, so the addition operation can always be performed bitwise parallel. The length of the remainder is always less than the length of the generator polynomial, which therefore determines how long the result can be. In practice, all commonly used CRCs employ the finite field GF2. This is the field of two elements, usually called 0 and 1, comfortably matching computer architecture. A CRC is called an n-bit CRC when its check value is n bits. For a given n, multiple CRCs are possible, each with a different polynomial. Such a polynomial has highest degree n, which means it has n plus a1 terms. In other words, the polynomial has a length of n plus a1. Its encoding requires n plus a1 bits. Note that most integer encodings either drop the MSB or LSB bit, since they are always 1. The CRC and associated polynomial typically have a name of the form CRCNXXX as in the table below. The simplest error detection system, the parity bit, is in fact a trivial 1-bit CRC. It uses the generator polynomial as a plus a1, and has the name CRC1. Application: A CRC-enabled device calculates a short, fixed-length binary sequence, known as the check value or improperly the CRC, for each block of data to be sent or stored and appends it to the data, forming a code word. When a code word is received or read, the device either compares its check value with one freshly calculated from the data block, or equivalently, performs a CRC on the whole code word and compares the resulting check value with an expected residue constant. If the check values do not match, then the block contains a data error. The device may take corrective action, such as rereading the block or requesting that it be sent again. Otherwise, the data is assumed to be error-free. CRCs and data integrity. CRCs are specifically designed to protect against common types of errors on communication channels, where they can provide quick and reasonable assurance of the integrity of messages delivered. However, they are not suitable for protecting against intentional alteration of data. Firstly, as there is no authentication, an attacker can edit a message and recompute the CRC without the substitution being detected. When stored alongside the data, CRCs and cryptographic hash functions by themselves do not protect against intentional modification of data. Any application that requires protection against such attacks must use cryptographic authentication mechanisms, such as message authentication codes or digital signatures. Secondly, unlike cryptographic hash functions, CRC is an easily reversible function, which makes it unsuitable for use in digital signatures. Thirdly, CRC is a linear function with the property that, as a result, even if the CRC is encrypted with a stream cipher that uses XOR as its combining operation, both the message and the associated CRC can be manipulated without knowledge of the encryption key. This was one of the well-known design flaws of the wired equivalent privacy protocol. Computation of CRC. To compute an n-bit binary CRC, line the bits representing the inputs in a row, and position the bit pattern representing the CRC's divisor underneath the left-hand end of the row. In this example, we shall encode 14 bits of message with a 3-bit CRC, with a polynomial xa³ plus x plus 1. The polynomial is written in binary as the coefficients. A third-order polynomial has 4 coefficients. In this case, the coefficients are 1, 0, 1 and 1. The result of the calculation is 3 bits long. Start with the message to be encoded. 11,10,11,101,100. This is first padded with zeros corresponding to the bit length n of the CRC. Here is the first calculation for computing a 3-bit CRC. 11,10,11,101,100. Input write padded by 3 bits, 1011 divisor equals xa³ plus x plus 1, 011001111001100. Result. The algorithm acts on the bits directly above the divisor in each step. The result for that iteration is the bitewise XOR of the polynomial divisor with the bits above it. The bits not above the divisor are simply copied directly below for that step. The divisor is then shifted 1 bit to the right, and the process is repeated until the divisor reaches the right-hand end of the input row. Here is the entire calculation. 11,10,11,101,100. Input write padded by 3 bits, 1011 divisor, 011001111001100. Result, 1011 divisor. 0111011111100. 1011, 0001011111100. 1011, 00011111100. Note that the divisor moves over to align with the next one in the dividend, 1011, 00011111100. 1011, 00011111100. 1011, 00011111100. 1011, 00011111100. 111, 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ɔ Since the leftmost divisor bit zeroed every input bit it touched, when this process ends the only bits in the input row that can be non-zero are the n bits at the right-hand end of the row. These n bits are the remainder of the division step, and will also be the value of the CRC function. The validity of a received message can easily be verified by performing the above calculation again, this time with a check value added instead of zeros. The remainder should equal 0 if there are no detectable errors. 11,10,11,11,101,100. Input with check value, 1011 divisor, 011001111001100. Result, 1011 divisor. 0111011111100. 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000011, 00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Remainder. Mathematics of CRC. Mathematical analysis of this division-like process reveals how to select a divisor that guarantees good error detection properties. In this analysis, the digits of the bit strings are taken as the coefficients of a polynomial and some variables are coefficients that are elements of the finite field GF, 2, instead of more familiar numbers. The set of binary polynomials is a mathematical ring. Designing CRC polynomials, the selection of generator polynomial is the most important part of implementing the CRC algorithm. The polynomial must be chosen to maximize the error detecting capabilities while minimizing overall collision probabilities. The most important attribute of the polynomial is its length plus 1 of any one term in the polynomial, because of its direct influence on the length of the computed check value. The most commonly used polynomial lengths are 9 bits, 17 bits, 33 bits, 65 bits. A CRC is called an n-bit CRC when its check value is n bits. For a given n, multiple CRCs are possible, each with a different polynomial. Such a polynomial has highest degree n, and hence n plus a1 terms. The remainder has length n. The CRC has a name of the form CRC nxxx. The design of the CRC polynomial depends on the maximum total length of the block to be protected, the desired error protection features, and the type of resources for implementing the CRC, as well as the desired performance. A common misconception is that the best CRC polynomials are derived from either irreducible polynomials or irreducible polynomials times the factor of 1 plus ax, which adds to the code the ability to detect all errors affecting an odd number of bits. In reality, all the factors described above should enter into the selection of the polynomial and may lead to a reducible polynomial. However, choosing a reducible polynomial will result in a certain proportion of missed errors, due to the quotient ring having 0 divisors. The advantage of choosing a primitive polynomial as the generator for a CRC code is that the resulting code has maximal total block length in the sense that all 1-bit errors within that block length have different remainders and therefore, since the remainder is a linear function of the block, the code can detect all 2-bit errors within that block length. If r is the degree of the primitive generator polynomial, then the maximal total block length is, and the associated code is able to detect any single-bit or double-bit errors. We can improve this situation. If we use the generator polynomial, where is a primitive polynomial of degree, then the maximal total block length is, and the code is able to detect single, double, triple and any odd number of errors. A polynomial that admits other factorizations may be chosen then so as to balance the maximal total block length with the desired error detection power. The beach codes are a powerful class of such polynomials. They subsume the two examples above. Regardless of the reducibility properties of a generator polynomial of degree r, if it includes the +1 term, the code will be able to detect error patterns that are confined to a window of contiguous bits. These patterns are called error bursts. Specification of CRC. The concept of the CRC as an error-detecting code gets complicated when an implementer or standards committee uses it to design a practical system. Here are some of the complications. Sometimes an implementation prefixes a fixed bit pattern to the bitstream to be checked. This is useful when clocking errors might insert 0 bits in front of a message, an alteration that would otherwise leave the check value unchanged. Usually, but not always, an implementation appends n0 bits to the bitstream to be checked before the polynomial division occurs. Such appending is explicitly demonstrated in the computation section above. This has the convenience that the remainder of the original bitstream with the check value appended is exactly 0, so the CRC can be checked simply by performing the polynomial division on the received bitstream and comparing the remainder with 0. Due to the associative and commutative properties of the exclusive OR operation, practical table-driven implementations can obtain a result numerically equivalent to 0 appending without explicitly appending any zeros, by using an equivalent, faster algorithm that combines the message bitstream with the stream being shifted out of the CRC register. Sometimes an implementation exclusive ORs a fixed bit pattern into the remainder of the polynomial division. Bit order. Some schemes view the low-order bit of each byte as first, which then during polynomial division means leftmost, which is contrary to our customary understanding of low order. This convention makes sense when serial port transmissions are CRC checked in hardware, because some widespread serial port transmission conventions transmit bytes least significant bit first. Byte order. With multi-byte CRCs, there can be confusion over whether the byte transmitted first is the least significant byte or the most significant byte. For example, some 16-bit CRC schemes swap the bytes of the check value. Omission of the high-order bit of the divisor polynomial, since the high-order bit is always 1, and since an n-bit CRC must be defined by an n-bit divisor which overflows an n-bit register, some writers assume that it is unnecessary to mention the divisor's high-order bit. Omission of the low-order bit of the divisor polynomial, since the low-order bit is always 1, authors such as Philip Koopman represent polynomials with their high-order bit intact, but without the low-order bit. This convention encodes the polynomial complete with its degree in one integer. These complications mean that there are three common ways to express a polynomial as an integer. The first two, which are mirror images in binary, are the constants found in code. The third is the number found in Koopman's papers. In each case, one term is omitted. So the polynomial may be transcribed as 0x3 equals 0b0011, representing 0xc equals 0b1100, representing 0x9 equals 0b1001, representing. In the table below they are shown as commonly used and standardized CRCs. Numerous varieties of cyclic redundancy checks have been incorporated into technical standards. By no means does one algorithm, or one of each degree, suit every purpose. Koopman and Chakravarti recommend selecting a polynomial according to the application requirements and the expected distribution of message lengths. The number of distinct CRCs in use has confused developers, a situation which authors have sought to address. There are 3 polynomials reported for CRC12, 16 conflicting definitions of CRC16, and 6 of CRC32. The polynomials commonly applied are not the most efficient ones possible. Between 1993 and 2004, Koopman, Castagnoli and others surveyed the space of polynomials up to 16 bits, and of 24 and 32 bits, finding examples that have much better performance than the polynomials of earlier protocols, and publishing the best of these with the aim of improving the error detection capacity of future standards. In particular, ISTC and SCTP have adopted one of the findings of this research, the Crc32 C Polynomial. The design of the 32-bit polynomial most commonly used by standards bodies, Crc32 IEEE, was the result of a joint effort for the Rome Laboratory and the Air Force Electronic Systems Division by Joseph Hammond, James Brown and Xiang Liu of the Georgia Institute of Technology and Kenneth Breyer of the MITRE Corporation. The earliest known appearances of the 32-bit polynomial were in their 1975 publications, Technical Report 2956 by Breyer for MITRE, published in January and released for public dissemination through DTIC in August, and Hammond, Brown and Liu's report for the Rome Laboratory, published in May. Both reports contained contributions from the other team. During December 1975, Breyer and Hammond presented their work in a paper at the IEEE National Telecommunications Conference. The IEEE Crc32 polynomial is the generating polynomial of a Hamming code and was selected for its error detection performance. Even so, the Castagnoli Crc32 C polynomial used in ISTC or SCTP matches its performance on messages from 58 bits to 131 kbits, and outperforms it in several size ranges including the 2 most common sizes of Internet packet. The ITU-TGHN standard also uses Crc32C to detect errors in the payload. The table below lists only the polynomials of the various algorithms in use. Variations of a particular protocol can impose pre-inversion, post-inversion and reversed bit ordering as described above. For example, the 32 Costa Rican colons used in both GZIP and BZIP2 use the same polynomial, but BZIP2 employs reversed bit ordering, while GZIP does not. CRCs and proprietary protocols might use a non-trivial initial value and final XOR for obfuscation, but this does not add cryptographic strength to the algorithm. An unknown error detecting code can be characterized as a CRC, and as such fully reverse engineered, from its output code words. C polynomial representations of cyclic redundancy checks for the non-hex representations of the CRCs below. Example implementations: implementation of 32 Costa Rican colons in GNU Radio. C-class code for CRC checksum calculation with many different CRCs to choose from. See also, mathematics of cyclic redundancy checks, computation of cyclic redundancy checks, polynomial representations of cyclic redundancy checks, error detection and correction, list of hash functions, information security, simple file verification, CKSUM, header error correction, references. External links, math pages cyclic redundancy checks, overview with an explanation of error detection of different polynomials. The CRC Pitstop home of a painless guide to CRC error detection algorithms, black, are fast 32 Costa Rican colons in software. The Blue Book. Systems Research Group, Computer Laboratory, University of Cambridge. Algorithm 4 is used in Linux and info zip and unzip. Kaunovis, M. Berry, F. A systematic approach to building high-performance, software-based, CRC generators. Inteller, slicing by 4 and slicing by 8 algorithms, CRC analysis with bit filters. Cyclic redundancy check, theory, practice, hardware, and software with emphasis on CRC32. A sample chapter from Henry S. Warren, Jr. Hacker's Delight. Reverse engineering a CRC algorithm, Catalog of parameterized CRC algorithms, Koopman, Phil. Blog, Checksum and CRC Central AA includes links to PDFs giving 16 and 32-bit CRC Hamming distances.